Hello all, welcome back. In the previous lecture, we have seen different atmospheric parameters and different relationships or the equations for finding out those relationships we have seen, such as vapor pressure, saturation vapor pressure, temperature, dew point temperature, and specific humidity. So, these type of different parameters which are required for studying atmospheric hydrology we have already seen. So, the basic requirements for doing the study on atmospheric hydrology we have seen. Now, let us see how this pressure and temperature varying as we go up into the atmosphere, because these details are required while we quantify the quantity of precipitable water. That means quantity of precipitable water means we all know moisture is present in the atmosphere. From that, after condensation we are getting the precipitation. Maybe it is rainfall or in some other form. We know we are getting rainfall from the moisture present in the atmosphere. So, we need to quantify how much is the mass of moisture which is present in the atmosphere. So, for that we need to have some interrelationship between pressure and temperature, and also how this is varying as we go up into the atmosphere. These details we need to get an understanding. So, we will start with that. So, first let us see the pressure and temperature variation in an atmospheric column. Initially itself we have seen for doing the analysis we need to have a frame of reference. So, that way we are considering a column within the atmosphere which consists of the moisture or moist air. So, that is the atmospheric column. You will be able to understand after you see the schematic representation of the atmospheric column. So, what we need to see now, we need to have an idea about pressure and temperature variation in an atmospheric column. Atmospheric column, that is, we are starting from the ground surface to surface and extending into the atmosphere. The depth of this column depends on the height to which you want to quantify the pressure, temperature, that way it will be varying. So, water vapor in the static atmospheric column we need to quantify. For that, consider a cylindrical atmospheric column. It is having a well defined area, cross sectional area A, that we are defining. We are considering an atmospheric column which is having an area of capital A. So, let us see the schematic representation of that column. So, this is the column which is having the area capital A. Now, what we are going to do? We are going to take two sections. One section close to the ground like this, and second section at some kilometers above the ground where the water vapor is present like this. So, the distance between these two sections depends on our analysis. So, section 2 is at some kilometers above the ground surface, that is the elevation of these two sections are Z1 and Z2. Now, what we are going to do, whatever analysis we are doing, initially we will be considering a small elemental strip, and the properties or quantities within the elemental strip will be calculated. After that, we can extend it to the entire column by integrating that particular quantity. So, in the similar way, here in this case also we are considering a very small elementary strip which is having a height dz in the atmosphere. So, this is the elementary strip which is having a depth of dz. Now, we need to know how much is the temperature and pressure corresponding to this dz. That is the variation of temperature and pressure as the altitude increases from the ground. So, dz you can see it is at a higher elevation than that of section 1, that is above the ground level. So, what we need to understand from this particular area of research is that we need to find the variation of temperature and pressure as we move up in the atmosphere. That is our main objective of this particular section. So, for that we need to have the understanding of two basic laws. These two basic laws we have already studied, that is basic laws that governs the property of water vapor in static column. First one is the ideal gas law and second one is the hydrostatic pressure law. Ideal gas law we have already seen before when we were talking about the pressure, vapor pressure and the total pressure. P is equal to rho A RAT, that P is representing the pressure related to moist air. That is why we are having a subscript A for all the terms contained within that. Now coming to hydrostatic pressure law. Hydrostatic pressure law you have already studied in the course of hydraulics, open channel hydraulics. So we will be assuming the pressure distribution to be hydrostatic in that case. As we go down from the surface in the open channel, we have seen pressure distribution is in hydrostatic form. In the similar way, here also we are assuming the pressure distribution to be hydrostatic in nature. So, if it is following the pressure distribution to be hydrostatic, it will be following the relationship like this. That is, as we go up, the pressure distribution is considered to be hydrostatic and P is given by P is equal to gamma H, you might have seen in hydraulics, that is rho g H. The same expression I am writing here, P is equal to minus rho A g z. Here our depth dimension is represented by Z and rho A is the density of moist air. Why negative sign is there? We are going in the upward direction into the atmosphere. That is why we are putting the negative sign. Otherwise, when open channel flow we were talking about, we were measuring into the water, that was in the downward direction. So, there we were taking positive. In the upward direction when we talk about pressure, we will be putting the negative sign. Now, we can get the expression for dP by dz. What will be dP by dz? dP by dz will be minus rho A g. We are just differentiating it. dP by dz is equal to minus rho A g. Now, we need to have the idea about variation of air temperature with altitude. This expression is also very much familiar to you, that is dT by dz is equal to minus alpha. Alpha is nothing but the lapse rate. What is lapse rate? It is the rate at which the temperature lapses as the altitude increases. Negative sign is there because as the altitude increases, the temperature is decreasing. So, dT by dz, variation of temperature with respect to altitude is given by a value, that is alpha, that is the lapse rate, and it is having a negative sign because as the altitude increases, the temperature is decreasing. Now, we are having the relationships related to pressure and also temperature. So, from ideal gas law we are having P is equal to rho A RAT, this is just repetition from the previous slide, and from hydrostatic pressure law we are having P is equal to minus rho A g z, and we have found dP by dz to be minus rho A g. So, here what we are going to do, we are having rho A, density of moist air, and here in this expression also we are having rho A. We will be making use of the expression based on ideal gas law to get the density of moist air, that is rho A is equal to P divided by RAT. So, this expression for density of moist air we will be substituting here in dP by dz. So, it will be taking the form minus Pg divided by RAT. dP by dz is equal to minus Pg divided by RAT. What we are going to do? We are going to separate the variables, that is we are going to take P towards the left hand side, dP by P is equal to minus G by RAT dz. Look at the expression on the left hand side, we are having dP divided by P, and on the right hand side we are having dz and T. So, we need to remove, somehow we do not want these two variables there, we need to make it in single one. So, we will convert this dz into in the form of T. Let us see how can it be done. Let this equation be 1. I am naming this equation to be equation number 1. So, from the Lapse rate equation, we have already seen the Lapse rate equation. From that we will try to find out some relationship between Z and temperature. So, dt by dz equal to minus alpha, this is the Lapse rate equation. So, dt by dz minus alpha, what we want actually, we want dz. So, dz is equal to minus dt by alpha. What we will do, this dz we will substitute in equation 1 for dz. So, the equation 1 will be taking the form dP by P is equal to, here also minus is there, in this equation 1 also contains negative sign. So, it will be positive. So, we will get dP by P as G by RAT dt by alpha. This is our expression for dP by P. So, we can see on the left hand side we are having the pressure and right hand side we are having the temperature. Now, what we can do, let this equation be number 2. Now, what we are going to do, this expression, this equation is for the elementary strip. So, if we want to apply it for the entire atmospheric column, we will be integrating it. So, we are going to integrate equation number 2, integral dP by P is equal to G by RA alpha integral of dt by T. What will be the limits? We will be integrating from section 1 to section 2. So, section 1 the pressure is P1 and section 2 it is P2 and temperature T1 and temperature T2. That is why the equation is integrated between, left hand side is integrated between P1 to P2 and right hand side is the terms related to temperature that will be integrated between T1 to T2. So, this is integral of P1 to P2 dP by P is equal to G by RA alpha integral of T1 to T2 dt by T. When we integrate this equation, it will be taking the form ln P integrated between P1 to P2 is equal to G by RA alpha ln T T2 T1 to T2. So, we are going to substitute the limits, it will be taking the form ln P2 minus P1 is equal to G by RA alpha ln T2 minus T1. This equation again we can modify like ln P2 by P1 is equal to G by RA alpha ln T2 by T1. Again some adjustments we are making in the equation to make it simple, that is we can write it in this way, that is P2 by P1 is equal to T2 by T1 to the power of, this will go to the power G by RA alpha. Then P2 can be obtained as P2 is equal to P1 T2 by T1 G by RA alpha. So, this is our relationship between P2 and P1. Look at this equation. This equation you can see on the right hand side, we are having P1, we are having T2, T1. Near the ground surface, P1, T1, that is the pressure and temperature we can measure, and we are having T2 term on the right hand side. T2 can be calculated, that is temperature at section 2 can be calculated by making use of Lapse rate equation. So, once P1 and T1 are known to us, T2 can be calculated, and by making use of this equation which we have derived now, that is the equation number 3, you can calculate the value corresponding to P2, that is the pressure at the section 2. Now, let us see how can we get the temperature. So, we will be making use of the Lapse rate equation, that is dt by dz is equal to minus alpha. We know two sections which we are considered are section 1 and section 2. Now what we are going to do? We are going to write the discretized form of this particular equation. We are having temperature at section 2 to be T2 and temperature at section 1 to be T1, and the altitudes are Z2 and Z1. So, this can be rewritten as T2 minus T1 divided by Z2 minus Z1 is equal to minus alpha. From this we can find out the expression corresponding to T2. So, T2 will be taking the form T1 minus alpha multiplied by Z2 minus Z1. Let me name this equation as equation number 4, and this is the equation, that is equation number 4 is the equation which is giving the relation of temperature with altitude. As we go up into the atmosphere, how the temperature changes. By making use of this equation, we can calculate the temperature at different sections if we know the temperature at a particular level. Also we need to have the idea about lapse rate, how much it is. Now we are going to see the schematic representation of this temperature and pressure variation as we go to the higher altitudes. Our relationship for T2 and T1, T2 is equal to T1 minus alpha Z2 minus Z1. Temperature, you can see T2 is T1 minus some quantity. So, definitely temperature at a particular altitude, higher altitude will be lesser than T1. At section 2 it will be lower than section 1. Temperature decreases as altitude increases. And look at this equation is in the form of y is equal to mx plus c. Forget about the sign, it is representing the slope, how it is changing. We know already as the altitude is increasing, the temperature is decreasing, that is why we are having a negative slope here. It is a linear relationship. Now coming to the pressure plot, it is given by this equation. Looking at the equation itself, it is very clear that it is a non-linear relationship. But while looking into the equation, you can see P1 multiplied by T2 by T1 to the power of G by Ra alpha will be giving you the pressure at a higher altitude P2 at section 2. So, P1 multiplied by T2 divided by T1. We have already seen from this relationship T2 is lower than T1. So, here numerator is T2, T2 divided by T1 to the power of some quantity. So, this will be multiplied with P1, you will get the value corresponding to P2. So, definitely P2 also will be lesser than that of P1. So, what we can understand from this? We can clearly understand that the pressure is also decreasing as the altitude increases. And the relationship is a non-linear relationship, it is not a linear one as in the case of temperature, and pressure decreases non-linearly as altitude increases. So, both the temperature and pressure decreases as we go up into the atmosphere. We need to have a clear idea about this while calculating the precipitable water in an atmospheric column. So, one particular atmospheric column we have considered, out of that how much moisture is available for us to quantify the precipitation. That is our main objective. That is why we have found out how this pressure and temperature varying as we go up into the atmosphere, because water vapor is present in the atmosphere. Now, we can have a plot how these are varying. Temperature is decreasing. So, I am going to plot the temperature variation as the altitude increases. Temperature decreases as the altitude increases in the atmosphere. We can plot the x and y axis. Along the x axis we are having the temperature, and along the y axis we are marking z, that is the altitude. So, section 1 we are having Z1, corresponding temperature is T1. In the similar way, corresponding to section 2, we are having Z2 as the altitude and corresponding temperature is lower than that of temperature at section 1. T2 is lesser than T1. So, I can mark it here like this T2, and this relationship is a linear relationship. The equation was in the form of a straight line. So, we can join these 2 points by means of a straight line like this. Variability of temperature as we move up into the atmosphere is linear, and as the altitude increases, the temperature decreases. So, the temperature variability with respect to altitude, that is Z versus T, can be plotted like this as a linear plot. Now, temperature variation is given by this Lapse rate equation dt by dz. What is it? Dt by dz is the slope of the line, slope of the straight line. That is nothing but our alpha. Negative alpha is there because it is sloping down. That is why we are having negative alpha, because temperature is decreasing as the altitude increases. And alpha is the Lapse rate, which is having the unit degree Celsius per kilometer of height. So, once this alpha is known to us, the slope is there with us, and the temperature at section 1 is known to us. We can calculate temperature at section 2. Based on that, we can get the variability in temperature at different sections or for different altitudes. The slope we can mark in the curve, that is alpha to 1, alpha vertical to 1 horizontal. So, this is the plot which is showing the variability of temperature. Now, we can plot the variability of pressure as the altitude increases. Same way we are proceeding, we are having the pressure along the x axis and altitude along the y axis. Corresponding to section 1, we are having Z1 and we are having a pressure P1. And in this case also, you should keep in your mind, at Z1 pressure is more compared to Z2 pressure at the section 2, that is P2. But the relationship is not linear as in the case of temperature. So, here in this case for section 2, we are having Z2 and corresponding pressure is lesser than that of P1. So, let me take this point as P2. It is not up to the scale, but for example, for getting an idea about the figure, I have plotted P2 here. Now, if I am plotting the pressure variation with respect to altitude, I have to look into the equation which we have derived, which shows the relationship between P2 and P1 is a non-linear relationship. It will be taking this shape. We can plot it by taking temperature, pressure, different values. When you plot with the numerical values, you will get the curve like this. And when we are talking about the slope, it is rho Ag to 1, rho Ag vertical to 1 horizontal, because we were having dP by dz to be minus rho Ag. dP by dz is what? It is representing the slope of the curve. So, temperature relationship is T2 is equal to T1 minus alpha multiplied by Z2 minus Z1, and pressure P2 is given by P1 multiplied by T2 by T1 to the power of G by Ra alpha. I hope it is clear to you the relationship between P1 and P2 and T1 and T2. The variables near to the ground surface, section 1 or the section which is close to the ground surface, will be having the values, measured values. Based on these values, based on the temperature at section 1, we can calculate temperature at section 2, and corresponding value of P2 can be calculated by using T2 and P1. Now, these relationships are required for us to quantify the precipitable water from an atmospheric column. We will be making use of the same atmospheric column, and we need to understand how much is the mass of the moisture present in the atmospheric column, which will be coming onto the ground as precipitation. Precipitable water in the static atmospheric column, that is the amount of moisture in atmospheric column. That is what is termed as the precipitable water. The water that can be precipitable as rainfall or in any other form, that is the precipitable water. So, this is very important. How much quantity of moisture is there in the atmosphere so that we can get this much of precipitation. That quantification can be done if we know the relationship which we are going to derive now. Same column we are going to consider, cylindrical column, which is having an area A, and we are considering similar sections, section 1, section 2. The altitudes corresponding to these sections are Z1 and Z2, and the height difference between these two sections can be taken as Z2 minus Z1. Now what we are going to do? We are going to consider an elemental strip which is having a thickness of dz within the column which is having cross sectional area A. Within this particular atmospheric column, we are going to consider an elementary strip. The depth of the strip or the height of the strip is dz. Small strip, that is why we are denoting it as dz. Now our main objective is to find out the amount of water in dz. That is what we are going to determine. And once we get the amount of water in this dz, we can integrate over section 1 and section 2 to get the total amount of water present in the column between section 1 and section 2. That is, we will be integrating at the end. Now let us see what will be the mass of air, mass of moist air present in the strip of height dz of that atmospheric column. We are having the atmospheric column dz. First we will find out how much is the mass of the moist air present in this elementary strip dz. How can we get the mass of a particular quantity? We will be having density. Density is mass per volume. So, mass can be obtained by multiplying volume with density. We know the density of air, moist air is rho A. The representation notation which we are using for moist air density is rho A. And if we multiply the volume of corresponding quantity, we will get the mass which is contained within that strip. So, rho A is the density multiplied by volume. What will be the volume? We know the area is A and the depth is dz. So, we can calculate the volume as A multiplied by dz. So, the mass of moist air present in this elementary strip will be rho A multiplied by A dz. Now next step is we have quantified the mass of moist air. Now we need to calculate the mass of the moisture presented or the water vapor present in that moist air. That water vapor is converted back to the precipitation. So what we will do? Because this thing we have already seen by means of a particular term, important term termed as specific humidity. What is specific humidity? It is the measure of moisture present in the moist air, right. That is the mass of the moisture divided by unit mass of the moisture to the ratio of the mass of the moisture to the unit mass of the moist air. So, we can get we are having the mass of the moist air, that is rho A into A dz. So, if we are multiplying specific humidity with this expression corresponding to mass of the moist air, we will be getting the mass of the moisture present in that particular strip. So, mass of water, here water I mean, it is the moisture present in that particular strip, that is dmp. Because it is a small strip, that is why we are denoting it by dmp. dmp is nothing but rho A multiplied by A dz multiplied by QV, our specific humidity. QV is nothing but our specific humidity. It is the measure of amount of moisture in atmospheric column. It is the measure of amount of moisture in the atmospheric column. We are having the mass of the moisture present in the elementary strip dmp. So, for the entire region what we will be doing? We will be integrating it over the particular depth. So, we need to calculate the mass of moisture present in the entire column. Total mass of precipitable water in the column between elevation Z1 and Z2, we will be integrating between Z1 and Z2 this particular equation. So, MP can be obtained by integrating rho A dz QV between Z1 and Z2. What we will do usually, this integral will be discretized and finally we will sum up all together. So, Z1 to Z2 we will be considering different strips within the column we will be considering, and each one will be, it is an approximation, but still if the depth of strip is very small, we can assume uniform properties or average properties can be taken. So, for simplicity what we will be doing, we will be discretizing and finally all these discretized values will be added up to get the total quantity of moisture present in the atmospheric column. So, integral is calculated using intervals of height delta Z. So, incremental mass of precipitable water in the strips can be obtained as, instead of MP it has changed to delta MP. Delta MP can be calculated by QV bar rho A bar A delta Z. That is this rho A between Z1 and Z2, that is the average value of rho A. And in the similar way QV also between Z1 and Z2, that is average value of this QV, and dz between Z1 and Z2, Z2 minus Z1, that is delta Z, that is what is written here. So, this is an approximation only, thinking that if we are considering a small strip, depth to be very small, it can be, even though approximation we are making, that will be giving you an accurate value. QV bar is the average specific humidity in the column of height delta Z, and rho A bar is the average air density of moist air in the column of height delta Z. So, the mass increments for different strips we will be calculating delta MP. These increments will be added together to get the total quantity of mass within the atmospheric column. That is, these are summed over the column to give the total precipitable water. And how can we calculate QV bar? QV bar can be calculated by taking average value QV1 plus QV2 divided by 2. And QV expression we have already found out in terms of vapor pressure and total pressure. QV is given by 0.622 E divided by P. So, QV1 is given by 0.622 E divided by P at section Z1 at the altitude Z1, and QV2 is the corresponding value at the altitude Z2, that is given by 0.622 E divided P at section Z2. Now, coming to rho A bar is given by average value of air density, that is rho A1 plus rho A2 divided by 2. What is rho A1? Using ideal gas law, we know the air density rho A as P by RAT. This P is known to us, temperature is known to us, we know the gas constant for air. So, rho A1 is obtained by using the expression P1 by RAT1. In the similar way, rho A2 is also given by P2 divided by RAT2. Rho A1 is P1 divided by RAT1 and rho A2 is P2 divided by RAT2. T2 is the value of temperature from Lapse rate equation, that is temperature at section 2 will be calculated by making use of the Lapse rate equation. P2 is obtained by using the equation derived earlier, because we have derived the equation for getting the value of P2 with respect to altitude, how it is changing we have already found out. So, that P2 relationship, P2 with P1 and temperature T1 T2, that equation will be used for calculating P2. So, these values are calculated for each strip and the corresponding delta MP will be calculated for each and every strip, and finally we will be adding up all these delta MP to get the total precipitable water. So, these are the references related to this topic which we have covered today. Please have a reading with any of these books. Derivation wise you can see from the applied hydrology textbooks. So, in today's lecture what we have seen the variation of the temperature and pressure, that is the important atmospheric parameters with respect to altitude. As the altitude changes, how the temperature is changing, how the precipitation is changing. We have derived these expressions by making use of certain laws, and we found that we have made use of ideal gas law, we have made use of hydrostatic law in the case of pressure, and in the case of temperature we have used the Lapse rate equation. By making use of all these things, we could derive the expression corresponding to temperature and pressure at section 2. And after getting the idea about variation of pressure and temperature with respect to altitude, we have seen the schematic representation of variation of temperature and pressure as altitude increases into the atmosphere. Then those relationships we have used for deriving the precipitable water in an atmospheric column. Precipitable water is nothing but the total amount of moisture which is available to us, which can be produced as precipitation. So, the quantity of the moisture which is present in the atmosphere, which will be converted back to precipitation, can be obtained by using the expression which we have derived in the previous slides. So, here I am winding up now. Next lecture we will see different types of precipitation and how this precipitation will be reaching to us. That is the precipitation water droplets when it is formed, with which velocity it will be reaching to us. This we will see in the next lecture. So, here I am stopping this lecture. Thank you very much.